Okay, so office hours today. A little bit crowded. Happens. So can I tell you the funny thing that's gonna happen? Quick story. Funny thing. We've got a midterm next week. Guess who's gonna show up to office hours next week? No. Usually office hours during midterms have less people in them. I think it's because for the homework quizzes, you know exactly what you want to ask. And then for the midterm, you're like, I don't know, I'm just going to study everything. And you don't have specific questions. And specific questions are what get people to show up. So what specific questions, number 9? I got a couple of emails about number 9, so I'm going to put number 9 on the list at least. What other questions do we have? Yeah.
17.
17. 19, 10, and 11. Any others? Everything else is easy? 14.
I agree.
You agree for 14?
Yeah. How were we supposed to finish this worksheet?
Wait, what worksheet? Oh, the homework?
Yeah.
Yeah, I thought you could finish all the homework. Can you not? I'm just checking to see. Okay, that should be good. 14, did I miss something after 14? Yeah.
The pH change.
Which number is that?
It's on your lecture slides.
Is it number 4?
It's 1 through 3, and it's like how much acid / base
Okay.
you need to change.
There's a homework problem like that as well. That's why I was asking. I think it's number 14. I'm not sure, but we can look at that as well.
Oh, it's 17?
Oh, it's number 17. Okay, we can look at that.
Yeah.
Others? This should be a good start. Let's start with number 9. Who's got what number 9 is?
Write a balanced net ionic equation for the reaction. And you want it's like A, B, and C.
What's one of the equations it's asking us to write?
Sodium hydroxide plus NaH2PO4.
So we're writing a balanced reaction.
And equilibrium. Water and Na2H2PO4.
Oh wait, I forgot a plus sign there.
Oh yeah.
Something like that?
Yeah.
Okay, we can put that this is going to be aqueous, this is going to be aqueous, this is going to be liquid, this is going to, no, that's aqueous as well. That looks like 2 cubes, but that's aqueous as well, right? So everything there should be aqueous except for the water, which is a liquid. We want to write a balanced net ionic equation for this. So if we look at this, you can see the sodiums are going to fall off. And this gets to a problem that we need to review from 127 to do this. And remember, I'm assuming that you remember everything from 127 and 128. I'm not assuming you remember it perfectly, which is why we do a lot of review, but I'm assuming you can at least have your memory refreshed quickly and I don't need to go over net ionic equations again. So when we look at this, we say, okay, what's the rules for which things break in water? Is water going to break apart?
No.
Why not?
It's in liquid form.
It's liquid form. But what's the important thing about it being a liquid form? Okay, let's try this one. Is sodium hydroxide going to break apart?
Yeah.
Yes.
Is it going to break apart into NaO and H?
No.
Why not?
Because the hydroxide aspect will stay together.
Why does the
Electronegative
hydroxide
oxygen.
aspect stay together?
Oxygen is electronegative. We'll hold on to that. Hydrogen bonds in water.
Well, the hydrogen bonds is an IMF. One of my pet peeves
Dancing rapids.
is when you refer to IMFs as bonds or bonds as IMFs. Drives me crazy. They're closely related to each other, especially with the really irritating one, hydrogen bonding, which is not technically a bond. Really frustrating, very easy to confuse people, but intermolecular forces are not bonds. But we're getting at the real trick here, so why doesn't this fall apart? Why does the Na and they OH fall apart from each other. What kind of bond was between them?
Oh, polar.
Well, not all.
No.
Way far end of polar, completely ionic. Right? Ionic bonds fall apart, but what's the other type of bond? Covalent. So the covalent bonds don't break apart, but the ionic bonds do. So we can say, look, the ionic bond between the sodium and the hydroxide breaks. The covalent bond between the oxygen and the hydrogen does not break. The ionic bond between the sodium and the dihydrogen phosphate will break, but the covalent bonds between the hydrogens and the phosphates will not. Now this gets into a little bit of a tricky area, which is why we need to review this for this quarter. Weak acids, these bonds kind of break, right? That's what's happening with donating a proton, is that hydrogen-oxygen bond can sometimes break. And in 127, we should have learned the trick that covalent bonds don't break, except for acids. Right? Acids were the special case, and since this entire quarter is looking at acids, we're gonna zoom in on this acidic behavior. But we're not going to break those covalent bonds. We're not going. So why doesn't water break apart? It's not because it's a liquid. It's because covalent bonds. Right? So those covalent bonds don't break. The ionic bonds do break, and I didn't give myself enough space, so the covalent bonds do not break. We can cancel out all the sodiums. So it's going to be OH minus plus H2PO4 goes to H2O plus HPO4 2 minus. That's the net ionic. And what it helps us do is it helps us zoom in on the chemistry that's actually happening. Proton donated, proton accepted. We've got an acid, we've got a Bronsted-Lowry acid, we've got a Bronsted-Lowry base, we've got a conjugate base and a conjugate acid. H2O is acting like a conjugate acid in this case because it is produced from the Bronsted-Lowry base accepting a proton. This covalent bond, now this is where we get a little bit extra, right? This covalent bond could break some. And that's where we get into the Ka, what we would call the Ka3 for this case, right? When we look at this covalent bond, we say this covalent bond could break some. That's the Ka2 for dihydrogen phosphate. We're not worried about that so much because OH minus with an H2PO4, that's just going to be a straight reaction. We're going to do the reaction, we're going to do the stoichiometry, and then we can look at the equilibrium of, well, these bonds might break a little bit or not a little bit, and then we would do the equilibrium to figure out that next part. But for writing a reaction, we're just looking at ionic or covalent bonds. Was that part A?
Yeah.
What's part B?
HNO3 plus.
Oh, is it just more reactions?
But
is there a particular one we should do?
I had a question on part C.
Part C?
Yeah.
What was part C?
Okay.
And everyone else, if you have the homework handy, it's helpful.
Uh,
And I've never seen it.
It's 2 NH4.
No, there's something left. 2 NH4.
Cl plus Ba OH2. And then
It's the OH2.
Oh, yeah. I was like, that doesn't make sense. There we go.
And then 2 water and 2 NH3.
there's also
And
there's a barium chloride.
Oh, two.
plus a barium chloride. Right? If I remember my states of matter correctly, aqueous, liquid, aqueous, BaCl, aqueous or solid? Aqueous, thank goodness. That would have made things interesting. Because, again, in 127, we learned about 3 types of reactions. We learned about precipitation, redox, and acid-base. We could do an acid-base reaction that is also a precipitation reaction at the same time. Just saying, could be a thing. You'd have competing equilibria in that case, Ka versus Ksp. But let's just look at this real quick. We can kind of start doing this in our heads, right? Barium's not going to matter. Chlorine's not going to matter. all that really matters here is the fact that we have 2 NH4 plus. That's going to be our proton donors. Plus, and I actually did that one wrong. What's wrong with this one up here? States of matter.
Oh, yeah.
Gotta have states of matter for it to be explicitly correct. 2 NH4 plus aqueous plus 2 OH minus aqueous. And that, sorry for my poor notation, I didn't give myself enough space again. It's going to go to 2 H2O liquid plus 2 NH3 aqueous. I'll try to be more responsible with my board use in the future. Again, this lets us accentuate the fact that we've got a proton donor in the form of ammonium, and we've got a proton acceptor in the form of hydroxide. And this will give us a particular reaction. Did this get to your question, or did you have something specific about this?
I just wasn't sure exactly how the NH3 would like split up.
Just like that?
Yeah.
Right, so this is a weak acid, and this is a weird way to write it down. NH4, we don't typically think of NH4 plus as a weak acid. We typically think of it as a conjugate acid, because NH3, ammonia, is a really common weak base. If we go to look up the Ka for NH4, we won't be able to find it. But we will be able to find the Ka for NH3 and say, oh, we can get between the two using Kw, that conjugate pair relationship we did on Monday. So that's problem 9. Just writing down reactions. Yeah?
Wait, so which would be the conjugate base and the conjugate?
So from the way we wrote down the reaction, this would be the, oh, that's Penstead. This would be the Bronsted-Lowry acid. This would be the Bronsted-Lowry base. This would be the, which one's the conjugate base?
Sorry.
So one of these is a conjugate acid, one of these is a conjugate base. Which one's going to be the conjugate base? Which one's the conjugate acid? Notice, in our previous problem, water was the conjugate, no, it was also the conjugate acid. It came out the same way. Water can also be a conjugate base, depends on which reaction we're looking at. Since these were both with hydroxide, water ends up being the conjugate acid. If we did this with H plus and some weak base, it could flip. Which one is the conjugate? Water can act like an acid and a base. It's part of why we had to do that whole auto-ionization thing. Question?
So NH4 in this case is our Bronsted-Lowry acid. Is it an Arrhenius acid?
If we look at what's the definition of an Arrhenius acid? Disassociates. If we put this in water, it would disassociate to NH3 and H plus a little bit. So technically, yes, this would fit for the Arrhenius acid definition, which is funny because NH3 would not fit for the Arrhenius base definition. Are we ready to move on?
Yeah.
Cool. Okay. So that was problem 9. Ooh, 10, 11. Why is it 10/11?
Is there serious?
Oh, is that the reaction in acid, reaction in base? No, what is problem 10? I can't remember the homework. It's been a while for me.
Write a pair of chemical equations for each compound to show whether the solubility of each of the following is affected by the decrease of pH and state if pH impacts solubility.
And then 11 is just
Yeah, and then 11 is something about increasing pH.
Yeah, I really got to make a note to myself. Note to self, watch this video and remember to fix problem 11. I made problem 11 and I'm not a big fan of it. But let's look at problem 10. That should be a pretty big hint that we'll probably won't have that on the quiz, but because I don't like the problem, but we'll look at it still. So if we're looking at problem 10, let's pick just, I think there's like 7 or 8 different ones.
7.
Let's just do A and B. What was compound A?
Silver chloride.
AgCl. What was compound B? SrCO3.
Okay, so in both of these cases, we're writing down a pair of chemical reactions, right? So we're going to write down two different things. There are some clues, and again, we want to look for clues in the phrasing of the problem. So let's read the problem again and think about it while we read it, if someone wants to read it out loud.
Write a pair of chemical equations for each compound to show whether the solubility of each of the following is affected by a decrease in pH, and state if pH impacts solubility or not.
There are three kind of key phrases that I heard in there, right? The fact that we're writing a pair of chemical reactions means I should be writing two separate chemical reactions. And then the question becomes, well, what two chemical reactions should I be writing? Well, it also mentions solubility, so I'm probably going to write something like a solubility reaction. And it also mentions pH, so I'm probably going to be looking for something that's like an acid-base reaction. Those are the hints for us that kind of guide us in the problem. And this type of problem analysis and practicing that is a really useful skill. Being able to pick apart a problem while you're reading it will make it so you go through all the problems at a faster rate, which is going to be handy on the midterm because we only have 15 minutes. Yeah, I'm scared too, don't worry.
So let's go ahead. Let's think about this. We're honing in on those three key terms.
We're thinking about pair, we're thinking about solubility, we're thinking about acid and base. Particularly with a decrease in pH, we're thinking acid-base reaction. So solubility of AgCl
would be going to
Ag plus.
Let's go ahead and just do both the solubility reactions, then we can come back and look at the next reaction. Since we're good with solubility, is not that hard, right? At this point, we're pretty great with it. Great.
okay. Strontium carbonate goes to easy, right? Now we have to do some thinking about what's going on here when we look at this. We say, okay, if we add H plus to this, I'm just going to put H. Well, let's do H3O plus. Let's be correct, right? Let's use the Bronsted-Lowry. Is H3O plus going to interact with Ag plus? Why not? They're both positive. Is H3O plus going to interact with Cl minus?
Yeah.
Could.
Is H3O plus going to interact with Sr2 plus? No, same logic, they're both positive. Is H3O plus going to interact with CO3 minus? It could. So now we say, okay, look, I've got something that's going to act like an acid. I've got something that's going to act like a base. I've got something that's going to act like an acid. I've got something that's going to act like a base.
I can write down an equilibrium here that goes to HCl. I can write down an equilibrium here that goes to HCO3 minus. We can put the H2O in there as well, so we keep everything
in a balanced acid-base reaction case. Now, what we have to say is this second reaction's equilibrium actually going to lie? And what we want to think about here is, if I affect the Cl minus concentration, will I affect the solubility? If I remove Cl minus, solubility has to increase. If I don't affect Cl minus, nothing happens. Same thing with this reaction. If I remove CO3 minus, the solubility has to increase to replace it. If I don't affect it, nothing happens. So what we want to think about with these second reactions is the solubility going to be, is the Cl minus going to be removed from solution? Is this reaction going to go towards this, or is it going to stay as Cl minus? For this first one, we can kind of just look at it and do inspection. HCl is a strong acid. So is it going to form? Will HCl, if we form any, what's instantly going to happen with the HCl? Disassociate. So if I wanted to write this arrow in a kind of cartoonish way, I would do it like that, right? I would have everything staying on the Cl minus, and the HCl would not really be changing at all. Like, I wouldn't form any of that. That is to say, my Cl minus concentration is not affected. Which is to say, I'm not going to change my solubility at all. Yeah.
So you said because HCl is a strong acid, it disassociates like completely. So when we form it, it's just going to go back.
Right. Right. So none of our equilibrium is actually that direction. I should make this arrow even smaller. Like, I can't draw small enough for how small that arrow should be. Right. It's all going to stay in the Cl minus case.
No question.
Yeah.
When it's asking about the solubility, like which solubility is it referring to? I'm kind of confused. The solubility of the Cl?
Well, so when it says, so if you read the question again, it says, how will the solubility of each compound, and AgCl is the first compound. So we're looking at how the solubility of AgCl is affected by decreasing the pH, which is introducing H3O+. Right? If the pH goes down, the H3O+ concentration is going up. So we're looking at how we're affecting the solubility.
Okay.
Turns out with AgCl, we don't affect the solubility. Yeah.
So say this was on the quiz, is it not enough to just like say H plus and like not do the H3O?
You could just do H+. I would let you slide. I know what you're trying to communicate. H3O+, and you know, that's going with the Arrhenius definition, which is still a valid definition for acids and bases. But doing the Bronsted-Lowry definition, you would have to do H3O+, so you have a donor and acceptor, and you're making your conjugates afterwards.
And so we know it's not, that the solubility is not affected because it creates a strong acid.
Yeah, and so that's kind of, you've already hit on the, this pen is still not working.
I want blue though. Putting formed.
So, if a strong acid is formed, no impact, right? Because a strong acid is not actually going to form, it's going to redisassociate right away. So, no impact. Let's go ahead and look at our second case, HCO3 minus. One of our strong acids? No. You're all shaking your heads no, but no one's saying it. No, that's not one of our strong acids, right? This is a weak acid. That means if we wanted to write this arrow in a kind of cartoonish fashion, we'd actually have to get the Ka to get how this cartoonish fashion would look, but we would have some significant equilibrium between the two. That means some of this CO3 minus, some of this CO3 2 minus will be removed from solution. If some of that CO3 2 minus is removed from solution, what happens to our solubility? Will solubility increase or decrease? Increase, right? We will need to have more solid fall apart in order to replace this. So we can come up with a second phrase. I'm putting this in quotes because I usually say this. If a weak acid is formed, pH decrease increases solubility. The other way you can look at it, you can technically do this without writing down two equations. However, if the problem asks you to write two equations, you have to write two chemical equations. But you can kind of do this without writing two chemical equations, and there's a way we can combine these two ideas into one sentence. It's looking at the anion of the solid. If the anion of the solid is the conjugate base of a weak acid, pH affects solubility. I think I've got that in a lecture slide we haven't gotten to yet either. If the anion of the solid is the conjugate base of a weak acid, decrease in pH affects solubility. So that's problem 10. And you can do the rest of those, right? You can do all those. Great. Because then it's just the same idea. You can just go down the list and not even write the reactions. You have to write the reactions to get credit on the quiz if I do this problem, because it specifically asks you to write 2 equations. But you should be able to just like read down and be like, oh, does this one, is it the anion a conjugate, is the anion conjugate base of a strong acid or a weak acid? And just go down them and just check. The reason I don't like number 11 is because the same simple logic doesn't exist. If you're increasing the pH, you can do that by removing H+, or you can do that by adding OH-, and you run into a bunch of precipitation problems. And you're really just looking, is the hydroxide going to form a precipitate or not? It's not really what I wanted the problem to do. I've got to think about that problem more. But you're essentially doing the same thing, except for you've got OH- and the plus thing interacting. So that's 10 and 11. Any other questions on 10 and 11? We can't really fit more people in here, can we? Can everyone just scoot a little bit closer though? Great. Okay. So that brings us to number 14. Let's see. We did 9, 10, 11. Number 14. Someone who has the homework handy, preferably who hasn't read yet. What is number 14 asking us to do?
Which solution has the higher pH? Give a qualitative explanation for your choice.
Keyword qualitative. Which means we don't have to do the math for any of these. So each of these is like A has 2 solutions, right? It's got a solution. What does part A say?
A 0.1 molar acid solution with Ka equals 1.1 times 10 to the negative 4th, or 0.1 molar acid solution with a Ka equals 4.8 times 10 to the negative 5th.
So there's a couple different things from the calculations we did on Monday. There's a couple different things we can look at and say, okay, what things affect the pH? What information are we given in the problem that might be good hints for what affects the pH? Right? Every time we did a calculation, if you did your ice table for initial pH, you're doing a concentration with a Ka, you're always getting something. We're not doing the actual calculation for this, but we're always getting something like Ka equals x squared over 0.1 minus x, but then we use the x is small approximation. We're always getting something like that, right? So it's the Ka, it's the 0.1. So when we have 2 things that are, so we can say the pH is affected by higher concentration means higher H3O plus concentration, right? And higher Ka also means higher H3O plus concentration. Because if our Ka is larger, it means more dissociation, means more H plus in solution. So at this point, we can look at this and say, okay, the concentrations are the same, so that's not going to affect it. All I have to do is consider the Kas. So the bigger Ka is going to be the one that disassociates more, so it's going to be the first one. And then we can just go down the list and consider each one independently, right? We can look at each thing and say, are the concentrations the same? Are the Kas the same? What's going on here? Yeah?
By higher pH doesn't mean the one that's more acidic.
You're right. Yes. Higher pH would be the one that's less acidic, so then we have to flip our thinking again. So I pointed at the one that would have the lower pH that's more acidic. So then after we have the higher H3O+, that would be a lower pH, and then we'd say this one And notice, I didn't do my logic wrong, but just thinking about the H3O plus concentration is not the same as thinking about pH. It's in fact the opposite because we get that negative log. So it's going to be the opposite of the thing that I just said. A is going to be the one that is more acidic, or sorry, the first solution is going to be the one that is more acidic, which is going to have the lower pH. So the second one is actually going to have the higher pH. Good catch. I almost messed that up.
I have a question.
Yeah.
Why does a higher concentration call for the lower, or how does it make it more acidic?
So higher concentration, if we did the calculation, that comes down to the calculation, right? We're always going to have this calculation of Ka equals x squared divided by 0.1. If this was 0.2, the square root would be a larger number. If this was 10, the square root would be a larger
okay.
number.
Thank you.
Yeah. Go ahead and look at this problem real quick. I think there's only ABC. Is there one that's still confusing in spite of this kind of thinking?
I have a question. So
Yeah.
if it has like a higher Ka, why is that H3 plus?
So again, this goes to the calculation, and this isn't asking us to do the calculation. Ka equals x squared over 0.1, right? So if I want to know what's going to make x larger, if I multiply this over, and we can even make this a little bit more simple, 0.1 times, if the 0.1 is larger, H3O plus is larger. If the Ka is larger, H3O plus is larger.
So that makes it like have a higher.
Ooh, that makes it have a higher H3O plus concentration, which would be a lower pH. Remember, the pH scale is opposite of H3O plus concentration.
I have a question.
Yeah.
For D, it has pKa.
Oh, pKa. Like I mentioned in class, I can't remember if that was Friday or Monday right now, but pKa, just like anytime we have the p function, it's negative log of Ka. And again, it's because the Ka values are always on the same, like 10 to the minus something scale. So it's often easier to talk about them in terms of pKa. However, again, because that negative sign is going to flip our thinking. Smaller pKa's are more acidic.
Thank you.
Yeah.
C talks about weak acid solution versus a strong acid solution.
So what information does weak acid versus strong acid give us? Is it information about the concentration or the equilibrium constant? Yeah, it's the equilibrium constant. A weak acid has a blank Ka.
Bigger. No, smaller.
Weak acid has a small Ka, or Ka less than 1 typically. A strong acid has a larger Ka, or a Ka that is greater than 1. That means the weak acid will always have the higher pH. Oh, assuming the concentrations are the same.
Yeah.
They are, okay. Because we could come up with a more complicated question, right? We could vary the concentration and the Ka, but then you wouldn't be able to do it qualitatively. You'd actually have to do the numerical analysis. You'd have to calculate it.
Would that be like a midterm type question, possibly, or? Do you
Oh
not
yeah,
know?
I mean, calculating pH, you should be pretty good at calculating pH. Yeah. But my point is, it wouldn't be qualitative, right? It'd be a calculation. Okay, so that was number 14. Any other questions on 14? Okay, 17.
Okay.
Yeah.
So 17 was talking about if you have 5.6 liter solutions, how much concentrated H3O plus or OH minus would you need to change the pH? And this has like A, B, C, and D.
Let's just do A.
Okay. A is a qualitative question asked in acidic. Do you change by adding H3O plus or OH minus?
Vote number 1 for adding H3O plus. Vote number 2 for adding OH minus.
Wait, to make it more, or
To change the pH, just to change the pH. Number 1 or number 2?
what was the options again?
In acidic conditions, are you going to add H3O plus or OH minus?
Just to change it? Like,
Wait, what? Can you read the question so I can make sure I didn't mess it up?
I don't have the real
Oh.
paper. I just
Oh.
wrote it on the white paper.
in acidic conditions, do you do a change in pH calculations in terms of H3O plus or OH minus? Why?
Sorry.
No, it's just
Because technically with the question I asked, it's going to be both, right? The pH could be changed by H3O plus or OH minus. We would add H3O plus if we want the pH to go down. We'd add OH minus if we want the pH to go up. However, when we want to think about what we're going to do the calculation in terms of, there's some simplifying tricks. If we're in acidic conditions, let's say we're at a pH equals 2. What's my H3O plus concentration?
It's high.
1 times 10 to the minus 2. What is my POH? What's my POH at that point? 12, right? 14 minus 2. That means my OH minus concentration is 1 times 10 to the minus 12.
If I did my calculation in terms of OH minus when I'm in acidic conditions, all my excess small approximations would fail, right? Because my OH change, anything I add would have this dramatic effect. So I'm going to look at whether I'm adding H3O plus to affect this or I'm adding OH minus to affect this. I'm going to do it in terms of interacting with the H3O plus. Because otherwise, this change is just going to, I'm going to have to do an equilibrium calculation afterwards for how the change in this affects the equilibrium of water with itself. So really what we're doing here is we're just doing a trick of recognizing that the H plus concentration and the OH minus concentration are related through water, right? Since I know these two are related to each other through water, that's what allows me to pick which one I want to do the calculation in terms of. And essentially what we're doing here is we're avoiding doing an extra equilibrium table. And I'm sure you're like, no, we want to do more equilibrium tables, but we can avoid it this time. So we're going to, if we're in acidic conditions, we're going to do this in terms of H3O plus. Now this was one of the problems I had up last time, and I was like, you can figure it out. Did y'all figure it out? Oh. That's okay. So let's see how hard it is to figure out. What is problem B? I'm assuming it's acidic conditions.
From 4.52 to 5.25.
Notice both are below 7, so both are in acidic conditions. If I have pH 4.52, what's my H3O plus concentration?
1 times 10 to the negative 4.52.
What is it?
Oh, is it 1 times 10 to the negative? No.
1 times 10 to the minus 4.52, but I want an actual number associated with it, because like we can get something that's a little, it's going to be like 5 times 10 to the minus 4. I can't do that in my head. Someone, calculators, help.
3.02 times 10 to the negative 5. That's the least of that.
Yeah, I was totally off doing that in my head. I'm still not that good at logs in my head. I'm working on it, but I'm still not there. So that is just 10 to the power of negative 4.52 gives us 3.02 times 10 to the minus 5. Then we're going to do the same thing with 5.25. (10 to the minus 5.25) is equal to
5.623 times 10 to the negative 6.
So we can notice a couple things here. Notice my H3O plus concentration is going down. which is not surprising because I'm going up in pH, which is a decrease in my H3O plus concentration. And I can just take the difference between these two to figure out how my H3O plus concentration is changing. So the change in my H3O plus concentration is
2.457 times 10 to the negative fifth.
Now, there's a couple thinking things we have to do. In order to have the pH go up, am I adding H3O plus or OH minus? When I add OH minus to something acidic, what happens? It reacts, the pH goes up. What ratio does the OH minus react with the H3O plus? 1 to 1. So how much OH minus do I need to add if I want to change the pH by that much? Whoa, I can't write all of a sudden. 2.457 times 10 to the minus 5. And then I'm going to also multiply by my 5.6 liters. And the reason this works is that we have a 1-to-1 ratio. There you go. If we wanted to think about this logically, we kind of have 4 cases. Acidic with the pH going up is what we just did. We can also do acidic with the pH going down. Acidic with the pH going down is easier. I mean, it's just the same thing, right? Because numerically it's the same, it's just logically it's a little different. It's just your H3O plus concentration. Just going to put acid in, so you're just changing your H3O plus. Then we can also do basic with the pH going up, which is you're going to do your calculation in terms of OH minus, and it's just whatever you calculate for your OH minus, that's how much base you add. And then you can also do basic for the pH going down. That is, you're going to calculate your OH minus and then do the same 1-to-1 ratio to get the H3O plus. And multiplying by 1 is not mathematically difficult. But notice the logic here is pretty tricky, right? We're adding base to affect H3O plus. We're adding acid to affect H3O plus. Whichever case we're looking at, whether we're doing pH up or down, varies what we are adding. Whether we're in acidic conditions or basic conditions varies what we do the calculation in terms of, so we can avoid that extra ice table where X is small fails. So with that in mind, we can do all of 10 and 11 now. Wait, no, not 10 and 11.
17.
We can do all of 17 and 18 now, right? Let's do another one from 18 just to make sure we can do it. And then we'll talk about the special case of 19 where you cross from acidic to basic. Guess what you're going to have to do? Do the calculation in terms of H3O plus, do the calculation in terms of OH minus, and then add them together. Asking about midterm questions. Crossing 7, good midterm question. But let's do another question. Let's do something from 18 just to make sure we understand what's going on here. So everyone look at 18, pick one that you think looks tricky, and let's do it together. The person watching left. I've always got one viewer because I've always got myself up. I don't know why they count yourself as a viewer. That's weird. In any case, let's do one from problem 18.
From 7.52 to 8.25.
Everyone happy doing that one? Anyone want to do a different one? I'm fine doing this one. So, notice we're in basic conditions. So we're going to do our calculation in terms of OH minus. So I'm going to go ahead and switch these to POH. I'm going to have trouble doing that in my head. 7.52 would be 6.48. 8.25 would be, I can't add to 14. 0.75. 5.75? Check me.
What did you just do for it?
I switched to POH. So all I did was 14 minus PH equals POH.
Okay.
I know that these two numbers need to add up to 14. These two numbers need to add up to 14. So I just did some mental math. The reason I did that is because then, if I wanted my OH concentration, all I have to do is 10 to the negative 6.48. And all I have to do is 10 to the negative 5.75. If you think I just did witchcraft and you're like, no, you take this number, you find your H3O plus concentration, and then you do 1 times 10 to the minus 14 divided by that also works, right? Those are mathematically equivalent. It's just whether you're doing it on the log scale or if you're doing it on the direct scale. But both should come out to the same numbers eventually. 10 to the negative 6.48.
3.31 times 10 to the negative 7.
And 10.57. 10 to the negative 10.5, or 10 to the negative 5.75, sorry. Saying the wrong numbers.
1.78 times 10 to the negative 6.
Then I just calculate my delta OH minus.
So,
Is everyone okay with the math that we just did?
so concentration OH is in negative 1.
Wait, so for the delta concentration, we're doing 1.78 minus to 3.31, right?
10 exponent.
Wait, say that again?
We're doing the right one minus the left one?
Right one, yeah.
Okay.
Right. So we could be really strict about which one's first, which one's last. I just do logic, so if I mess up my negative signs, I can still fix it because I can do the logic of what I need to add for how the pH is changing. I know the pH is going up, so I must be adding hydroxide. And I must be adding hydroxide enough to get this change. So I'm adding my change in hydroxide concentration is 7-ish. I can't do that in my head. Wait, 17, 14-ish. 1.4 times 10 to this. What is it? What is it?
1.44 times 10 to the negative 6.
Doing math in my head is
Fine, but
actual calculations are better. This is moles of OH minus per 1 liter.
then we multiply. This is also in 5.6 liters.
Yeah, same.
So then we would, if we were asked for the number of moles we need to add, we've got to multiply by 5.6 liters. Notice again, oh sorry, question.
Oh, I was gonna ask a question that kind of relates to this. For D, it goes in the opposite direction. The pH goes down, but it's still a basic solution.
So we're going to do the calculation the exact same way. We're going to find the moles of OH minus change, and then just say because of the 1-to-1 ratio, we're going to be adding H3O plus.
Okay.
Right?
So
It's-
whatever.
yeah, go ahead.
So like whatever number we get for like our OH change is gonna be the same for the H3O, but just opposite sign.
Wait, same, but
Never.
it's the same magnitude, right? It's
Yeah.
always the same amount of change, and because it's a 1-to-1 ratio, it's going to be same stuff. So we should be able to do all of those. If we wanted to do is it number 19 where we cross 7?
Yeah.
So if we want to do number 19 where we cross 7, you do a calculation. So you essentially break up the problem. I'm not going to actually do it.
However, we'll set it up. What's number 19? Is there only one for number 19?
Yeah.
I figured I only gave you one because it's a longer calculation. So for number 19, we're going from pH. No, I don't know. Someone
Oh,
please tell me.
5.34 to 8.97.
So notice the first thing we have to realize is because the pH is going up, we are adding OH minus.
But we're going to split this problem up into two parts, 5.34 to 7, in terms of H3O plus, and then from 7 to 8.97 in terms of OH minus. And again, the reason we do this is we're essentially avoiding doing an equilibrium table, right? We're using the fact that we know the equilibrium of water already, and we're avoiding an equilibrium table. It's also not just avoiding an equilibrium table, but it's avoiding an equilibrium table where you would have to solve the quadratic.
I have a question.
Yeah.
For the first one, 5.34 to 7, why is it in terms of H3O plus?
Is this acidic conditions?
Yeah.
Yeah, so we're going to do, because it's acidic conditions, we're going to do it in terms of H3O plus and recognize that we have a 1-to-1 ratio,
Oh, okay.
right? And then from 7 to 8.97, we're going to do it in terms of OH minus, and then it's OH already.
And then do you just add the two together?
Add the two together, done. Right, so if we could do problem 17 and problem 18, problem 19, it's really the only thing that's tricky about this is realizing that we have to do this separation to make it so we don't run into the extra small equilibrium issue. Right? When we're in the acidic conditions, H3O plus dominates the equilibrium. And so we can just look at H3O plus. When we're above 7, OH minus dominates the equilibrium, and extra small approximation works, so we can ignore the equilibrium essentially. Not ignore it, but we don't need to worry about doing a separate calculation. Now, one of you could raise your hand and be like, oh, but what about at 7? Technically, anywhere close to 7, all of our approximations that we use for water start to break down a little bit, and we should be a lot more careful. But since we're just going past it, we're okay. If I asked you to do a calculation from like 6.8 to 7.2, we would end up having a kind of serious problem, because that small amount around where the equilibrium of water is significant would totally mess with us. We'll notice in a lot of the calculations we're going to do when we start doing titration curves is we do things that try to make it so we can avoid doing calculations right at 7. Yeah.
How come we can add them together in the end if one is H3O plus and one is OH minus?
In terms of H3O plus, but we're going to recognize, I'll put it in green here. So we're going to do it in terms of H3O plus because H3O plus is going to dominate the equilibrium, but then we're going to recognize that there's a 1-to-1 ratio to convert us to OH minus. Right? So that is this situation where you're acidic. So you do the calculation in terms of H3O plus, but your pH is going up, so then you convert it to OH minus using a 1-to-1 ratio, recognizing the fact that H plus plus OH minus just makes H2O. So I can remove H3O plus just by adding OH minus.
So at the end, our answer's gonna be all like totally in terms of OH.
Because the pH is going up, it has to be all in terms of OH. Because if you had half of it, I added 3 drops of acid, then I added 3 drops of base, that would just cancel out what you just did. Right. But good question, right? And that's we really want to be doing that kind of nuanced thinking, because again, the mathematics we're looking at, none of the mathematics are particularly tricky, but the concepts and ideas and how we connect those ideas to the mathematics, that's what becomes really important. Did this cover the lecture slides for you as well?
Yeah.
Yeah, because I think that was problem 17, 18, 19 was the lecture slide question you were asking about as well. Did anyone have other questions that we haven't gone over yet?
Can we go over 15?
Sure. What's problem 15?
For each solution, calculate the pH and pOH and identify if it's acidic or basic. is it a basic or neutral? Or I don't
Let's
know if
pick
I-
let's pick one of the solutions.
Can
I look at? I want to see.
yeah.
Oh. So what do you notice about all of the solutions in problem 15?
They all either have an OH or like a common one, either an acid or base.
They're all strong acid or strong base. So that means if we're looking at a strong acid, whatever the concentration is equal to right? Because a strong acid completely disassociates, whatever the concentration of the strong acid is the H3O plus concentration.
Okay.
Same thing, whatever our strong base is, that's going to be directly equal to our OH minus concentration, with the exception of those double hydroxide ones. You're going to have to double it. You can come in too. There's more space. People left. There's like space. So, right, if you've got something that's got 2 hydroxides, you're going to have to double, right? You have to take into account mole ratio here.
Okay.
I think all of the strong acids in that problem are monoprotic, and I think there's one that's a diprotic, a dibasic, but I have a note next to it even.
Which approximation fails?
So, just saying that it completely, you know, it's a 1-to-1 ratio fails because it's not 1-to-1.
Okay.
Any other problems? So we did 17, 18, 19, 15. Is there anything we haven't done yet that people still want to see? In that case, I'm gonna stop the video for now. I'm gonna stop the YouTube lives. Oh, 3 people are watching now though. It's a little blurry. Keep the autofocus thing back on. So many things to make this work.
Are you going to upload this video?
Yes, I will. Ooh. Focus just went nuts. There we go. Sorry about messing up the focus there for a minute. It's back focused now.
Oh, yeah.
I think I can focus a bit better. People who are watching live, do you have any questions? Because I was about to stop it and then upload the old stuff. Talking to people who aren't in the room. This is the part of doing this that I can't get used to. There we go. Okay. Yeah.
I'm confused on how to know if it's like a conjugate acid or a base.
How do we know if it's a conjugate acid or a base? So let's go over the definitions of those things, right? So the thing to keep in mind with a conjugate acid and a base is we can't actually define a conjugate. If I just wrote, let me see if I can think of one. If I just wrote HC2O4 2 minus, oh sorry, just minus, not 2 minus. And I said, is this a conjugate acid or is this a base or is it an acid or is it a base? Something by itself, we can't define the conjugate. All we can say about this is it fits the definition of a Bronsted-Lowry acid and it fits the definition of a Bronsted-Lowry base because it can accept a proton or it can donate a proton. It's when we write this down in some reaction where let's say we have H2O and this goes to H2C2O4 plus OH minus. In this case, this thing is acting like a base water is acting like a Bronsted-Lowry acid because it donates a proton, and then this becomes the conjugate which one? Acid or base?
It's accepting a proton.
Uh-huh.
It's a base.
Ooh, so this is accepting a proton. This behaves like a base. Notice, does this thing have extra protons it could donate? So if I'm looking at these two, these are the conjugates, right? The oxalate and the oxalate are the conjugates. And I'm just figuring out which is a conjugate of which. This thing accepted a proton to become this, which means if I went the other direction, this thing could donate a proton. So this is going to be the conjugate acid. So essentially, it's kind of considering this arrow going both directions, right? This direction, it acts like a base. This direction, it acts like an acid. This is the Bronsted water, acts like a Bronsted-Lowry acid donating. Hydroxide is going to act like a conjugate base going the other direction. Just to mess with you, we can do the same compound and consider its other behavior. Right? So I can also look at HCO, oh, that's not the same compound, HC2O4 minus plus H2O, and I can say, oh, this goes to C2O4 2 minus plus H3O plus. In this case, this thing is donating a proton, so it's behaving like a, yeah, so this is going to be a Bronsted-Lowry base. Wait, no.
Acid.
Donates a proton. Acid. Whoa. I got all the way through writing base before I was like, no, that's not right. But you said it so confidently, I just believed you. Then, when we look at this thing, if this thing, can it donate a proton?
No.
It can only accept a proton. So if we looked at it going the other way, this would be the conjugate. Well, that's and this would be the conjugate base. If we looked at H2O in this case, H2O is accepting a proton. So in this case, water is acting like a Bronsted-Lowry base. And this would be the yeah. And we can clearly tell that's the acid because H3O plus is an acid. And we could even draw these little connecting things so that it's more clear which things are connected to which. Right?
So as a conjugate, like base or acid, just kind of consider it going the opposite direction?
Pretty much.
Okay.
Right? So it's recognizing this fact that this thing that behaved like an acid, you end up producing something that can behave like a base. And vice versa. Right? And this really hones in on the fact that we're doing equilibria now, right? We're no longer just talking about things going one direction. We really have to think about how things can go forwards and backwards at all times. Which is buffers. Yeah?
How would you know which equation to write? If you're
So if I just said, here's HC2O4 minus, which one do you do? Well, it depends on what we're investigating about the compound. If technically both of these equilibria can both be happening at the same time, right? We can look at the, let's see, this is behaving like a base. We can look at the Kb associated with this, and we can also look at the Ka associated with this. This would be the Ka2, and this would be the Kb1. I know this is the Ka2 because this is losing the second proton. I know this is the Kb1 because it's the base of the first proton.
What did you just say?
So I labeled this one as Ka2. It's always easier for me to think about the acidic behavior because the Kas are all labeled in terms of the acidic behavior. This would have Ka1 because that's losing the first proton. This has Ka2 because it's losing the second proton. So I call this Ka2. Since this is Ka1, I know this must be the Kb1 because it's the conjugate pair of the first proton. So this is Kb1, this is Ka2. And I could look at how each equilibria plays a role at different pHs, different OH minus concentrations, different H3O plus concentrations. Because technically both are happening. We're going to be operating when we get to, we're not quite at polyprotics, I'll jump the gun a little bit, but when we get to polyprotics, we're going to be dealing with this situation where it's obvious which one we're dealing with, or if we're dealing with the other one. So we're going to have different regions where we can essentially deal with only one of these equilibria or the other. And we're not going to deal with this middle section where the two are competing. That goes back to the calculations where we avoid doing things close to 7. Anytime we've got these steep jumps, all of our approximation methods fail, and it's really hard to do the calculation. So we avoid those steep jumps. And we'll get to that in a couple more days. Probably by the midterm. Maybe by the midterm. Let's see. No questions. Okay. Okay. I'm going to go ahead and stop the live stream. Thanks for watching. I will put up the video right now so you can watch it later.